Welcome to this heat transfer lecture on convection. We're going to start talking about external convection. External convection basically means convection when you have fluid flow that is unbounded, like flow over a plate or flow around a cylinder or flow around a sphere, as opposed to internal convection, which would be like flow through a pipe or flow through a channel. So if you recall, convection is heat transfer from a surface, typically a solid surface, to a fluid. So it's the theory of how does thermal energy get from that surface to the fluid, or vice versa. A lot of the focus on convection at the undergraduate level is going to be focused on how do you determine H, which is the convective heat transfer coefficient, as we used in Newton's law of cooling. So far, as we've talked about H, we've used it a little bit in energy balances and at the boundaries of conduction problems, and we've always treated H as if it's a constant. But as we discovered in the last chapter, H can be something that varies. So H is going to be a function of the geometry of the system, of fluid properties, and a few other parameters. So this is going to be the basic procedure that we follow to find H for the next several chapters in the book. So first we evaluate the geometry. So we want to look at what's the geometry for external convection. Again, this is going to be flow over a flat plate. There could be different thermal conditions of the flat plate. It could be isothermal, or you could have constant flux. It could be flow around a cylinder or flow through banks of tubes, and a couple of others. So first we want to figure out, okay, what's the geometry? That'll help point us in the right direction for which correlation to use. Then we want to evaluate the fluid flow conditions, so things like the Reynolds number. Hopefully you're familiar with the Reynolds number from your fluid dynamics classes. So the Reynolds number is a dimensionless number that helps describe flow, so that can tell us if the flow is laminar or turbulent, for example. And whether the flow is laminar or turbulent makes a big difference for heat transfer, so we want to determine how the fluid mechanics of the system influence the heat transfer of the system. As you can imagine, and as we've discussed, turbulent flow has a lot more circulation and a lot more mixing, so that tends to be really enhances heat transfer. Another dimensionless number that we'll discuss is called the Prandtl number. The Prandtl number, represented by PR, is it's a property just of the fluid itself. So if you have water will have a specific Prandtl number at a specific temperature. This is something you could look up in a textbook or online. Our textbook has an appendix that tells you Prandtl numbers for specific fluids. And in addition to those numbers, we'll also want to make sure that we're using the appropriate temperature when we evaluate the fluid properties. So the temperature definitely influences some of these properties, so we want to make sure we know which temperature of the fluid to use. After we know the fluid flow conditions and the geometry, we're going to want to plug that information into correlations. So these are going to be usually empirical correlations, but in general mathematical correlations that tell us how does our heat transfer coefficient vary as a function of those things that we just discussed. So we're going to use the appropriate correlation to find something called the Nusselt number. So the Nusselt number is another dimensionless number, which we'll talk more about in a couple of slides. The Nusselt number is basically a dimensionless heat transfer coefficient. So a lot of the correlations, you want the correlations to be generally applicable to a lot of different fluids. So rather than doing experiments or solving analytical equations to find H for a specific scenario, you can generally lump parameters together and you can find the Nusselt number, and then using the Nusselt number you can back calculate to find H. So the Nusselt number, because it's a dimensionless heat transfer coefficient, it can also be a local heat transfer coefficient or an average heat transfer coefficient. And we'll get into more about that soon and have more examples. Once you know the Nusselt number from a correlation, you would then use the definition of the Nusselt number. So the Nusselt number is defined as H, the heat transfer coefficient, times L, which is L is going to be a characteristic dimension, typically a function of the geometry, over K sub F. This actually looks quite a bit like the BO number, however it is very different. So the key difference here is this subscript here. So the K that we're looking at is the thermal conductivity of the fluid and not the thermal conductivity of the solid, as in as we looked at in the BO number. So this is more a ratio of convective heat transfer in the fluid versus pure conductive heat transfer in the fluid. So once we have backsolved to find H, we know that H can be local or average. So this is something just to store away. Some of this may not be particularly meaningful to you yet until you go through this process a few times, but this will be basically the process that we'll use as we're trying to find H in chapters 7 through 10, essentially, of the book. So just to give you an example, you'll find these correlations as we develop some of the theory and some of the conceptual understanding, but this is basically what they look like. So here are conditions about our geometry. This is a flat plate. This particular correlation is for turbulent flow and constant heat flux. So you can see we're looking at the geometry and the fluid flow conditions. Then we're going to plug that information, including Reynolds number and Prandtl number, and knowing that this is constant flux and a flat plate, for example, we will plug that information into this correlation. This correlation will give us our Nusselt number. So you see that we have the Reynolds number and the Prandtl number both showing up in this correlation. So we'll go back and show you where these correlations come from, but I just wanted to give you a sense of where we're going with this. So chapter 7 on external convection is going to develop a lot of different correlations. This is just a partial list. It's not comprehensive. But you can see we have different geometries like a cylinder in cross flow or fluid flow around a sphere. So we'll go through and sort of show where these come from. A lot of the times they come from just experiments, so the equation itself may not be super physically meaningful. So it's important to just sort of remember this general procedure, and that's a big part of the focus of convection. Because convection gets extremely complicated, a lot of the time it's difficult to come up with clean, sophisticated math from a purely analytical standpoint to represent convection. So often we have to resort to experimental results where we gather data and then fit that data to an empirical correlation. Okay, so let's talk about some of these dimensionless numbers. Hopefully you are familiar or getting familiar with the Reynolds number. So the Reynolds number is the ratio of inertial to viscous forces. It's a function of geometry, fluid flow, and fluid properties. The typical definition of the Reynolds number is rho is the fluid density times fluid velocity times L over the fluid's viscosity, mu. So rho and mu are fluid properties, V is a function of the fluid's flow, and then L is a characteristic length. So you're probably most familiar with the definition of Reynolds number as rho v d over mu, where d is the diameter of a pipe. This L changes depending on the geometry. So for flow across a flat plate, that characteristic dimension is actually x. So the Reynolds number actually changes depending on how far you are down the length of a flat plate. And we'll talk more about that later. Another way of expressing the Reynolds number is in terms of the kinematic viscosity. So the kinematic viscosity is not defined as the dynamic viscosity over the fluid density. So this term is also known as the momentum diffusivity. So this is a measure of how well momentum propagates its way up through a fluid, just as the thermal diffusivity is a measure of how well heat propagates its way through a fluid. So these are analogous. So that brings us to the Prandtl number. So the Prandtl number is specifically the ratio of the momentum diffusivity, or the Greek letter nu, divided by the thermal diffusivity, which is the Greek letter alpha. This is also the same as heat capacity times viscosity divided by thermal conductivity. So just a couple of different rearrangements of variables. So the Prandtl number is a dimensionless number. Again, it's something you can look up in an appendix of a book or online somewhere. So it's a function of the fluid properties. So as you're going through these correlations, you'll need to figure out what the Prandtl number is. Then you'll need to calculate the Reynolds number, and you'll plug both of those and maybe some more variables into these correlations. Okay, the Nusselt number, as we introduced on the last slide, is the ratio of convection to pure conduction heat transfer in the fluid. So as we've talked about convection, remember, so convection is caused partially by advection, where you have a circulating fluid that as that fluid moves, it carries its own internal energy with it wherever it goes. So that circulation and mixing of the fluid, known as advection, is a big part of convection. However, remember that conduction can also happen in a fluid. If you have a stationary fluid, then conduction by that same microscopic molecular motion can happen in the fluid. So that is partially happening too. So really, convection is the combination of advection and conduction. So this Nusselt number is a measure of how much convection is happening. So convection as in the total heat transfer phenomenon in getting heat from a surface to the fluid versus how much of that heat transfer is happening just by pure conduction. And again, this is different from the BO number. The BO number is the ratio of convection in a fluid to conduction in the adjacent solid, whereas the Nusselt number is the ratio of convection in the fluid to the conductive effects in that same fluid. So I wouldn't get too hung up on the definition here. Just know that you'll need these dimensionless numbers so that you can calculate H. So really, this slide is the one to really remember, and then you'll start to build a library of these different correlations as we go through the discussion of all these different scenarios. So the Nusselt number is a function of geometry, fluid flow, and the fluid properties. So there are a lot of dimensionless numbers. These are three of the critical ones that you should get familiar with. And again, I'm less concerned about memorizing the physical meaning of these. Just know that these are things you need to calculate so that you can calculate your H eventually. So this is the definition of the Nusselt number, but if you recall, the correlations give us Nusselt number, so then we have to back solve from that. So we end up getting, so we run the correlation to get the Nusselt number, and then we apply the characteristic length and the thermal conductivity to get H. So you'd get something like H is equal to the Nusselt number times K over L. Okay. So let's introduce some of these correlations. So I mentioned that typically they are empirically determined. However, when you have a really simplistic system like laminar flow over a flat plate, in those particular scenarios, there is some math you can get and get some use out of analytical solutions. And I misspoke. Let's talk about the Nusselt number first. So the Nusselt number is a dimensionless heat transfer coefficient. It can be local. Just like H can be local, Nusselt number can be local too, so it doesn't have the bar on top. That represents a local heat transfer coefficient. Or it can be averaged over the entire surface. So just like H can be averaged, so can the Nusselt number be an average. This can be a function of distance. So the Nusselt number, if it's a function of distance x, then the Nusselt number, you may see this subscript x, and it just means Nusselt number is a function of x. Or it can be a function of the diameter of a pipe. So if it's a Nusselt number describing heat transfer around a pipe, then you might see this d subscript. Again, I wouldn't get too hung up on these little subscripts. Just remember sort of the basic meaning and, more importantly, the utility of the Nusselt number. So again, the Nusselt number is HL over K, and you just back solve that equation with some really simple algebra to get H as a function of the Nusselt number arising from your correlation. So average Nusselt number has the bar on top of it. The subscript just means that the Nusselt number is evaluated over that particular distance L. Again, with the heat transfer coefficient, the bar above it means that's the average heat transfer coefficient over the entire surface. L is the characteristic dimension that you're talking about. So here, L is a subscript. It doesn't have a mathematical representation in this equation, but here, L is an actual variable with units that you need to multiply your equation by. And then K sub F is the thermal conductivity of the fluid and not the solid. So getting onto analytical solutions. So to actually obtain an analytical solution, and we'll just walk you through one example so you can see what goes into it. So these require that you have pretty simple geometries, that the flow is purely laminar, and that you have constant thermal properties. And then even with those restrictive assumptions, they're still fairly complex to solve. I'm not going to get too detailed into the math because I don't think that's particularly important. If you are intellectually curious about it, you can feel free to read about it more in your textbook. What we are dealing with when we're solving for some of this information analytically, we not only have energy conservation to consider. So here is an energy balance of our system where now, because we have advection happening, we have to deal with heat transfer by advection. So we have this u, which is the velocity in the x direction, and v, which is the velocity in the y direction. Those both show up in the equation. So it's a reasonably complex PDE to solve, just the energy balance. Coupled with that energy balance, we also have the momentum balance to solve, and then we also have a mass balance to solve simultaneously. So all of these partial differential equations are coupled, and they must all be solved simultaneously, so that gets really tricky. So they're all assuming laminar flow, and if you recall, when you have laminar flow, this is the flow over a flat plate example. Because of the viscous forces, you get this no slip condition, which means that your fluid velocity right at the plate is going to be 0, and then the boundary layer thickness is a relative measure of it's a measure of how far up the plate in the y direction you have to go before you reach the free stream velocity. Similarly, we also are going to be solving for the thickness of the thermal boundary layer. So the thermal boundary layer, you're going to have this constant temperature boundary condition here. But remember, when we're dealing with convection, we're looking at h times delta t, where delta t is the delta t from here up into the free stream. So the boundary layer thickness is a measure of how far away do you have to get from the surface of the flat plate in the y direction before you get to 99% of your free stream temperature, or your bulk fluid temperature. Okay, so what's happening in these boundary layers? So we've treated convection. If you remember, Newton's law of cooling is the flux equals h times delta t, and the delta t, again, we're looking at is from the surface temperature up here. And we've treated that as just a sudden change in temperature, just a sudden temperature drop. But as you can see from the plot here, there's actually more of a gradual change that's happening. And this boundary layer basically describes what's happening in terms of temperature when you're very close to the plate. So we're going to go quickly through a solution here. I personally don't get too hung up on the math. It's not something that I think you'll retain long term, but it's consequential to know sort of the origin of where these equations come from when you can get, in the rare case where you can get an analytical solution. So here is how this solution is obtained by some mathematicians. So they define what's called a dimensionless temperature, which is the relative rate of temperature change relative to the overall temperature difference, T infinity minus the surface temperature. So it's the temperature at a particular y, or a particular height above the surface. So this would be a number between 0 and 1. Similarly, we're also going to use the dimensionless velocity, u over u infinity. So u is the fluid velocity in the y direction, and u infinity is the fluid flow in the y direction once you get high up enough above the plate that you are in the free stream. So the way this happens is they create a new parameter called a similarity parameter, represented by the Greek letter eta. So this is just the definition. I don't find this this definition to be particularly intuitive. Just know that these are some mathematical transformations that make it so that you can put those coupled PDEs into a form that you can actually solve. So they put this into this form where f comes from this definition. So u over u infinity is df by d eta. So they put this into this form, do some transformations, and they go about getting a solution out of this. Again, I consider this to be outside of the scope of an undergraduate heat transfer class. If you are interested, you can go to section 7.2 in our textbook to get a full derivation of this, but rigorous solutions, I consider this to be outside of the scope of our class. So let's look at the solution, though, and some things that come out of it. So after you've solved these equations, you end up solving for the boundary layer thickness at any given x. So if you remember, when we have flow down a flat plate, our boundary layer grows. So this equation is basically telling us how does that boundary layer grow as a function of x. So interestingly, you'll note that that is a function of the Reynolds number. So the boundary layer, the velocity boundary layer thickness is going to grow in proportional to x divided by the Reynolds number to the 1/2 power. So this delta, if you recall, is the velocity boundary layer thickness. The Reynolds number is, so this RE represents the Reynolds number. Notice the x here. So our characteristic dimension that we're considering for flow over a flat plate is x, or how far are you down the length of this plate. So the Reynolds number shows up that L, that characteristic length for flow over flat plate, becomes x. So the Reynolds number is defined as rho Vx over mu, or Vx over nu if we're using the kinematic viscosity version. So notice that the Reynolds number is growing the further you get down the flat plate. So unlike fully developed fluid flow in a pipe, where the Reynolds number is just constant as long as the velocity and pipe diameter are constant, the Reynolds number actually gets bigger and bigger as you go down the length of the flat plate. And if you remembered, at some point this flow transitions to turbulent. So here we have the laminar region, here we have the turbulent region, where suddenly that boundary layer thickness gets thicker because you have all this extra circulation going on in the fluid. So we can actually characterize when that transition happens by looking at what's called a critical Reynolds number, and that critical Reynolds number is the point when your flow transitions from laminar to turbulent, and we'll talk about that more later. Other useful things that come out of this similarity solution are the friction coefficient and the shear stress. So those are things you should be learning about from your fluids class. We won't use those definitions much in this particular class, but we will be particularly interested in the parameters down here. So the thermal boundary layer thickness is given by delta T, and you can see the ratio of the momentum boundary layer thickness to the thermal boundary layer thickness is proportional to the Prandtl number to the 1/3 power. And if you remember, the Prandtl number was the ratio of momentum diffusivity to thermal diffusivity. So basically, if you have a higher momentum diffusivity resulting in a higher Prandtl number, that means your fluid is more viscous, and your those viscous forces will be stronger, your boundary layer will be thicker and thicker. If your fluid has a really high thermal conductivity or really high thermal diffusivity, which are going to be proportional to each other, then your thermal boundary layer thickness will be bigger and bigger, meaning the heat is propagating through via conduction much faster than convection, which is going to be caused by the bulk fluid motion. So that delta T is the thermal boundary layer thickness. We've got our Nusselt number down here. So as I want to point out, going through this solution, we actually come away with a really useful correlation for Nusselt number. So this comes out of the analytical solution, and again, this is the rare case where you can actually solve for Nusselt number analytically. So this comes out of that. So this particular correlation is a function of the Reynolds number and the Prandtl number, as we discussed earlier, and you would basically look up the Prandtl number for the fluid, you would calculate the Reynolds number, you would plug and chug. So this is a plug and chug type of endeavor once you've figured out the right correlation to use, and that gives you Nusselt number. So Nusselt number, notice that it doesn't have the bar on top of it, so that means this is a local Nusselt number, and this x means your Nusselt number is going to be a function of x. When you have flow over a flat plate and you're plotting your Nusselt number itself may be a function of x. Well, it will be a function of x. So that tells you, so you can see the locality here. We have a higher Nusselt number here and a lower Nusselt number here, and those are just rough kind of hypothetical plots. Okay, so just looking at how the similarity solution looks when you plot it. So here we are plotting y over delta. So this is how far up you are from the plate in the y direction. So here's the y direction. And then on the bottom we have our normalized or our unitless fluid velocity. So basically this is just a velocity profile. So so depending on the boundary layer thickness, this is how your velocity profile will look like. So notice this is all relative to delta. So here's how that would look. Then let's look at the temperature profiles. So similarly, we have the same coordinate on the y-axis, basically how high up you are from the plate. And here we have this additive inverse of our normalized temperature. So basically, if this is a heating situation, you would get the hottest temperatures here, and you would get the lowest temperatures up here. So we have this plotted for different Prandtl numbers. So if our Prandtl number is 1, if you remember that correlation, so if our Prandtl number is 1, then we get delta, or the velocity boundary layer thickness, over delta t is equal to 1, meaning that momentum and heat diffuse through our fluid at the same rate, essentially. So our boundary layer thicknesses are going to be the same. So if our Prandtl number is exactly 1, the momentum diffusivity and the thermal diffusivity are equal, and so their boundary layers end up being the same thickness. And that is shown here. If we look at this center line, we see that our Prandtl number is 1, and we see that our thermal boundary layer thickness is going to be 1 there as well. And this is a unitless thermal boundary layer thickness. It's going to be the same as our velocity boundary layer thickness. So if you have a Prandtl number that is greater than 1, so here on this bottom line the Prandtl number is 7. So the Prandtl number is the ratio of the thermal diffusivity, momentum diffusivity to thermal diffusivity. So if our Prandtl number is 7, that means that momentum propagates through this fluid a lot better. So we're going to have a thicker velocity boundary layer and a relatively thinner thermal boundary layer. So it's good to develop a little bit of intuition around these kind of things. It's not mission critical. You can kind of rely on the equations to get you where you're going to go. And somewhat unfortunately, that's sort of the treatment of convection through this course, is that we're relying on correlations, and sometimes, so convection gets so complicated. There are so many different things going on with energy, momentum, and conservation of mass going on that the mathematical treatment of it can be extremely complex. And so rather than dealing with this extremely complex and sophisticated calculus, we end up using empirical correlations and just sort of relying on a plug and chug kind of mentality.